If we're right that there's no quantum mechanics and it's all about ratios of separations between points in Euclidean space, that's where these miracles of entanglement could come from. You will now go to cosmology courses and they will talk about space expanding. I am frankly very suspicious about that. This is the complete inverse of what you think of from all the entropic ideas. Order emerges out of disorder, and it gives a theory of rods and clocks, which general relativity has got nowhere near creating yet. It's going to be completely different if you allow for infinitely many particles. This theory is a little bit like many worlds, but it's many shapes. There's one shape in which the cat is alive and one in which it's dead. The cosmological principle is a holy grail of cosmology. It comes straight out of this. This quantity here, the variety, that ratio there, that's intrinsic. If you use the same ruler for measuring both of these quantities, you'll get the same result. And then Einstein himself, he called it a sin that he hadn't done that. That all emerges beautifully in the Newtonian theory, nothing but ratios. If you look at all the work that was done developing thermodynamics and statistical mechanics, there's always implicit a box. I think there's only one person before me who asked, what happens if there's no box? As the universe gets older and older, its structure gets richer and richer. I mean, when I was born, I had, very smooth skin and no hair. I mean, I'm beginning to look a bit decrepit, but I've got much more structure in me now,
Hello, everyone. Welcome to the event with Julian Barbour and myself, Maria Violaris. Apologies for the delay, but we are starting now. So just brief introductions before we dive into some very interesting ideas to do with quantum mechanics or getting rid of quantum mechanics, as you'll see. Just to introduce ourselves, I am a quantum physicist and I finished my PhD in the foundations of quantum information last August in Oxford. That was with Vladimir Vedrov's group, and I was looking at some of these issues like the arrow of time and so on that Julian will be mentioning today. Now I work in quantum computing, but also foundations, and I have a YouTube channel and post content like this on there, which is why I'm filming today. Julian, would you like to give us a brief intro to yourself?
Yes, well, as I think I've already said, I got very interested in the nature of time and motion back in 1969 after I'd finished a doctorate, and decided academia was not the place for me. It was already publish or perish then. So I could earn my living, as it happened, by translating Russian scientific journals, which I did for 28 years, but it gave me time to develop my ideas. I was very lucky. I got a very good collaborator, and then further I would go to scientific conferences, and for me it turned out absolutely perfect, and I'm still sort of working away in that line. What I want to talk about today is, the way I put it, I think my main collaborator, Tim Kozlowski, and I may have stumbled, I use the word, the principle of creation. And I'll illustrate why I say that. So that's a major part of the talk. Now, if we're right, this is going to be a huge change. But even if it's not vindicated, because nothing in science is certain, I think it's still extraordinarily interesting what we've come across. So let's sort of, let me just get going and say how I start. So perhaps we can have the next slide.
So just to outline the structure, Julian split the topics into 3 parts. So we'll do Julian will present part 1, then we'll have discussion about that from myself and hopefully questions from all of you. So please keep them in mind as we go. And then we'll have part 2 and then part 3. So we'll split it up that way, and we can get started with presenting part 1.
Yeah, so that's this incredibly beautiful house I was lucky enough to buy. Let's go on to the next slide, because then we'll really start getting into things there. About a year or two ago, I got something prompted me to start thinking about consciousness. And I've come to think that maybe consciousness has very seriously misled theoreticians. The first one is about time and motion. Now, you see me sitting here, but if I move my finger like that, you see the motion as well. And basically, at least since Newton, but I would say long before that, position and momentum in physics were put on an equal footing, ontological footing. But I think could be that we are not questioning that nearly enough because of the way, because you literally see my finger moving. But for over 25 years, my conjecture has been that as you see my finger moving, the reality is that in the pattern of my neurons, there are, as it were, 6 or 7 snapshots of my finger, and they're all sitting there, and they are like stills in a movie, and consciousness plays the movie for us. So that's going to suggest now that everything in physics that uses motion and momentum to explain phenomena should be questioned and perhaps eliminated. So this is going to be a very rigorous project which can have has the potential to completely change the way we think about physics. So that's the first thing there. So so that, as you see, I say, it says it leads to the idea of dynamics and causality. So the standard view is that the present state of why I'm here now is in the distant past there was some state which evolved in accordance with dynamical laws, and this resulted in the present situation. So that's the first thing that I think needs to be challenged. The second one is, in fact, if you draw with black ink a curve, what I signed the book for Maria, you write with black ink on white paper, you can see what clearly looks like a continuous curve. But the reality is, actually, it's a lot of fermionic particles all packed together that are creating that thing there. It's actually discrete. It's a discrete set of things there. But that notion of continuity led Leibniz and Newton independently at the same time to create the differential and integral calculus. And that then opened up all of the things that you can do with field theory, the electromagnetic field. So it led on to Riemannian geometry, field theory, and wave functions. And I think that might all have come about because theoreticians, very great ones, were misled by consciousness. And so the question is it possible to explain all the phenomena with a vastly simpler ontology, basically just points in Euclidean space? Now, you may think that's going to be completely impossible, but at least one thing I will say, if it works, it's going to make life a great deal simpler, because it's modern physics with wave functions and dynamically evolving geometry is not simple. So that's the air. So now what about evidence? Now, the reality is every evidence we have for anything about the universe is all contained on solids. I mean, John Bell makes this point. All the results of quantum experiments, in a way, they're often just printed out on A4 paper. It's letters on A4 paper. So that is the evidence. Even the spacecrafts that have now left the solar system and sending back information there, the information is here on the surface of the Earth, and to an extraordinarily good accuracy, nobody's going to question the validity of Euclidean geometry on the surface of the Earth for these things there. So that's the nature of the evidence. Now, a very significant part of my presentation is going to be about scale invariance. So I'm going to introduce scale invariant functions, and they're going to be ratios of the separations between particles. and they will be pure numbers. So that's going to be the theoretical thing, finding these functions, these scale invariant functions that do the trick and reproduce what we know. And the one thing about this is it's relatively easy theoretical work to think about these functions. I'm only going to present you the simplest one of all, but it's very remarkable what it does. And then I think that you will take that seriously. But then the other thing which I'm finding now, and it has already in part been done, is that what these functions predict can be tested extraordinarily easily with modern computers. And in fact, somebody is working on that in Lisbon now. She's already making interesting progress. So in fact, if this is right, it might reduce expenses and things incredibly, and also time. So we'll see. But that's the possibility. Let's see how far I can get in persuading you. So that's why I'm saying consciousness is clearly a gift. I would say that it has been very honest in telling me that there are angles between points I see. As I look out, I see lots of pairs of eyes, and I see small angles between them. That, I take it, is an accurate reflection of reality. All the rest, I say, is possibly suspect, and we'll see how far we get with that. So let's go on to the next slide. So I'll just, all of this has come from me reading Leibniz back in 1977 and being hugely impressed with what he said. Two things. In his correspondence with Arnaud, he introduces the concept, the complete definition of any contingent thing. And he says that to define a contingent thing like Adam, it's no good saying Adam was a man, because there were lots of men. And it's no good saying Adam was a man in a lovely garden, because that's true of other men as well. And he said, when you have to list all the attributes of any contingent thing. And when you've done that, you have finished up by describing the whole universe from the point of view of that contingent thing. And then in his monadology, this was very influential for me, and also for Lee Smolin. He talks about variety. This is why I've now adopted a word, variety. And just as the same town, when looked at from different sides, appears quite different and is, as it were, multiplied in perspective, so also it happens that because of the infinite number of simple substances, it is as if there were as many different universes, which are, however, but different perspectives of a single universe in accordance with different points of view of each monad. But that is the means of obtaining as much variety as possible, but with the greatest order possible. Now, in fact, actually, if you have a point in Euclidean space and lots of other ones, the attributes of each point that define it are actually the angles it sees to the other points. So the complete attributes of the point are the angles that it sees relative to the other ones. So that's how I see that. I have some feeling I may have slightly modified the slides. Never mind, this will do. We go on. Let's go on to the next slide, if we would. Now, I think actually this is where we take a break at this point. Yes, that's there. So this would be a good thing for any questions at this stage. Maria, you want to start with any comments?
Yeah, I'll try and kind of recap my understanding of the ideas and see if I've got the right idea. Would you mind flipping back to let's start with the consciousness slide. So here you're presenting the idea that, so one question I have is kind of exactly the connection you're making between the consciousness and the observations and ontology. What was the link there exactly, like you mentioned with say drawing a black line? What was the connection with consciousness? Could you expand on that?
Well, we just see the line as a continuous curve. and I think it's quite clear that when Leibniz and Newton invented the differential calculus, they thought that it was appropriate to model the world with continuous curves. But if the world just consists of points, which you can think of as particles, then that is very far from the way that the world is. So you are introducing something into your description of the world which just isn't there. And it's certainly the tools that developed out of that then led on to what Riemann was able to use when he created Riemannian geometry, Faraday, and above all Maxwell, and he created field theory, and then quantum wave functions. All of that, the mathematics really goes back to the Newton and Leibniz, starting with the idea of a continuous curve. And all of the mathematics, that's where the mathematics came from. But maybe that was just going in the completely wrong direction. Maybe that's not what it was like at all. Maybe the reality is much more like when we look at the night sky and just see stars scattered on the sky. And in fact, theory began in a way with the ancients trying to understand how the constellations got the shapes they did, and they introduced this incredibly beautiful story of Orpheus and Eurydice, how he lost her because he had to turn around and look at her, and the constellation for that is the harp in the constellation Lyra. So this was theorizing, and by the way, with shapes. So shapes are going to be the beginning and end of all this story. So, and if you read, I recently read Lucretius, I've got halfway through Lucretius's De Rerum Natura on the nature of things. It's quite clear if he's an accurate reflection of the early atomists, which people say he was, their primary concern was to explain shapes. Why do all sheep look the same? Why do children look like their parents? And for each of these macroscopic objects, shapes that look the same, he postulates atoms, indivisible, solid, and he has a different shape for everything he needs to explain. So I think the primary drive in science initially was to understand shapes. And I'm rather saying, well, we should go back and at least think about that seriously, and think about it as just points separated by distances.
Mm-hmm. So in this shift between like continuum and discrete, how is it connecting to consciousness? Is it kind of via the observation aspect? Well, it's just that one of the aspects of consciousness is that I see, when I signed the book for you, I see my name, as Shakespeare would say, blank ink on white paper. And that was it. But the reality is certainly not a continuous distribution of there. It's fermionic particles. It's sitting on the top of the paper, and the paper itself is made of fermionic particles with separations between them. Now, according to standard physics, it's the Pauli exclusion principle that keeps them from not being all on the same point. But we'll find there's a possible alternative explanation of that when we get through to it. Mm-hmm. Yeah, so you're saying that we see things as a continuum when it's actually discrete? That's discrete, yes. Mm-hmm. Now, what I do allow is I allow the ratios of the separations between the particles to change continuously, but they're never to be a continuous curve. So the Newtonian n-body problem, the first non-trivial dynamical theory, it's just about point particles in Euclidean space moving relative to each other, and the objective content is entirely in terms of ratios of those separations. There's a quantity called the root mean square length, so you take each separation, each Rij between particles I and j, and you divide it by the root mean square length of the complete system, then you've got a pure number. And the Newtonian n-body problem is just about that and nothing else. So I'm actually going back to the original one. So could you just there's some reason to hope. Yeah. Could you briefly summarize the n-body problem for someone that might be unfamiliar with what the problem actually is?
Well, this again well, there's a very interesting thing about this, is that in 1907, a Swedish mathematician, so first of all, the people who've studied this mathematical problem have been guided from right back what happened with the Babylonians, from present observations to predict the future when eclipses would happen. So that was the key task. But so that always was looking to what can happen in the future. And Sundman asked, in the case of the three-body problem, the first non-trivial problem, is it possible for all three particles to collide at once? That's not the ratios, it's just the with an external ruler. So if you have a triangle, you normally think it has a shape and a size. But if the three particles are the entire universe, only the shape can be meaningful, because the size would require a ruler in addition to the universe to measure it. So this is a pernicious mistake, I think, that still runs through physics, to think that there are absolute distances. It goes back to Newton's notion of absolute space, which has an implicit notion of absolute scale. And what Sundman showed was that the three particles could all collide in terms of an external ruler. But to do that, the angular momentum of the three particles had to be zero. And secondly, as they come together, as that size measured with an external ruler goes to zero, the shape has to become very special. Either it must become an equilateral triangle, or it must come collinear with one of the three possible ordering of the particles. So that was 1907. A year later, it was extended to an arbitrary number of particles. And the really interesting thing is we'll come to this, it's actually a ratio of two numbers, each of them presupposing an external ruler, but it's the ratio of those two numbers tends to a finite number, and the shape becomes very special. Now, rather remarkably, it seems I was the first person seriously to realize that by the time reversal symmetry of Newton's equations, you can time reverse that. And if you do that in the standard way of thinking, it's a Newtonian Big Bang, discovered theoretically 20 years before Hubble was making his observations. So, and by the way, that shows how shape is very important, because that ratio of those two lengths that are measured with an external ruler, then their ratio is a pure number, and that pure number tends to a finite limit, and it defines a shape. And so this is where the reality is about shapes, I would say. And so I think if you're worried of me getting rid of all sorts of things in Newtonian, in physics with field theory and so forth, there's some pretty wonderful stuff in the Newtonian n-body problem, which virtually nobody knows anything about. I've been very lucky to interact with some of the very best people who work on the Newtonian n-body problem. But lots of other people know. I don't think any of the serious cosmologists know anything about these Newtonian Big Bangs. And by the way, they reproduce as they evolve. They look very like how our universe has actually evolved. And there's no inflation or any of those strange things with quantum squeezing during inflation and so forth. So I think that's food for thought.
Yeah. Can we just flick to the next slide, Mia? Thanks.
Yes. Now we come to this key quantity. Yes. So.
So is that for the next part?
Yes, this is.
Yeah, we can just pause for
people from the audience. Yes, sure.
Yeah. Does anyone have any questions, comments on anything that's been mentioned so far?
Have you come
I'll
across
pass you the mic.
Sorry.
For the video to get the recording in.
Have you come across causal set theory?
Sorry?
Causal set theory. Have you come across
Yes, and I don't believe in it.
Okay. Do you want to
Because
say
there's no
something about
geometry. Galileo said, "He that attempts natural philosophy without geometry is lost." I've never been persuaded by causal sets, I'm afraid. And in desperation, they have these causal sets and then they sprinkle them into into Minkowski space to try and make sense. I think Galileo got it right. He that attempts natural philosophy without geometry is lost.
Any
Apologies to Faye and Raphael Sorkin.
Any other questions or comments so far? Okay, I think we're ready to move on to variety. So
yes, yeah. Right. So yes, we haven't quite got the rearranged slides, but these will do. So now this is the key question, and this again comes entirely from me thinking about Leibniz saying variety. Without variety, there's nothing in the world. And so the question is this: given points in Euclidean space, what scale invariant function, I'll call it variety V, of the separations of finitely many points in Euclidean space might characterize the extent to which they are uniformly distributed or clustered? So this is exactly a little bit like when you go out at night and look at the constellations and the stars. There are clusters of stars, and then there are wide spaces and things like that. How would you quantize that? How would you quantify that on the bowl of the sky? Or alternatively, if you're wandering around in three-dimensional space, how would you do that? So to be scale invariant, it's got to have length dimension 0, and one way to get that is to have two lengths that are have dimension, two quantities which have the dimensions of length, and you take their ratio, and that will give you a pure number which is scale invariant. And there are two obvious candidates for that. I've already mentioned the first one. That's the root mean square length. So if A, B, and C, and then any others are the separations between all the pairs of particles, you take the square, you square it, and then you take the square root. That's the root mean square length. And then that's one. And the other one is the mean harmonic length, and it's the inverse of this quantity. Now, you could weight these with masses. Now, if you added masses, you would have particle A and B, you would have the masses of A and B, and B and C and so forth. You would have masses there and here. And actually, if you put the masses along there, you would actually get the Newton gravitational potential. So the mean harmonic length is the inverse. When you've got masses in there, it's the inverse of the Newton potential. So that's there. So then to get a pure number, you just take the ratio. You divide the root mean square length by the mean harmonic length, and that's what comes out there. Let me say something about this quantity here, because I was emphasizing this intuitive way people think that there's an absolute scale. So and I would call that an extrinsic scale. But this thing is an intrinsic scale. This quantity here, the variety, that ratio there, that's intrinsic. It's a pure number. It doesn't rely upon any external, whichever ruler you use. If you use the same ruler for making for measuring both of these quantities, you'll get the same result. So it's about as honest a number as you can get. And in fact, as it changes, it's a positive definite quantity. That's really going to be critical. This is a positive definite quantity with an absolute minimum, which corresponds to the most uniform shape that you can have. And as clusters form, it's just like what happened according to our observations in the universe. Clusters formed, and this quantity, what I call the intrinsic scale, gets larger. And I believe that's the way one should think about expansion of the universe. You will now go to cosmology courses, and they will talk about space expanding. I am frankly very suspicious about that. I think that this is Well, of course, you can do that if you've assumed and you've given ontological reality to curved space, which you can't see. But if it was in terms of particles, you would see what this ratio doing, what I call the variety there, and you will see that that is growing. And I will show you when we get into the third session, a bit further on, I'll show you literally how that happens. You can see the universe expanding before your eyes. Now the interesting thing is here, I've rewritten this in this particular way, taking each of the terms in the mean harmonic length and put it underneath each of all that lot here. So if you have a huge number of particles, you've got the root mean square lengths of all of them, that huge thing, and underneath each of them is the separation between each pair of particles. And this makes this quantity incredibly sensitive to the separations getting small. This is going to, if we're right, if we're going in the right direction, how this might transform physics, that's going to be absolutely critical, that fact that it's the 1/r for each term there that is going to do that. So if I want to find a distribution of points, and somebody like Maria has said the value of your variety function has got to be this number to a very precise accuracy, it's going to be incredibly difficult to adjust the separations like that. It's what I call a holistic William Tell problem, because you just one of them anywhere gets too close and you've overshot the mark. You've got too big a value for the thing. So it's holistic, and it requires very precise tuning. And that has colossal impact in what comes out of this. If we're right, this explains why I can sit on this chair. It will replace the Pauli exclusion principle. So let's go on.
Yeah, maybe I can ask a few questions on this slide. So what was the kind of motivation for constructing it out of these particular quantities? Like, are they kind of the unique way to construct this quantity? Or is there a way of kind of checking that it's the right quantity to get the clustering?
Well, what happened was, from my specialists who work in the n-body problem, particularly Alain Albury at the observatory in Paris, I did learn about this quantity, which they call the shape potential or the normalized Newton potential. This is the one place that I know in physics where a quantity like that is taken seriously, but not in the way I've taken it.
Right.
And then I thought, how might Leibniz have come up with that number? And that's how he would have, that's how he could have, Leibniz could certainly have come up with that expression to do that. And the interesting thing is, it's exactly the two numbers that govern that are the beginning and end of the Newtonian n-body problem. This is the inverse of the Newton gravitational potential, and the other is the quantity that measures its size. So the Newton n-body problem is all about how those two numbers vary. So there you have, as I'd like to say, those two bitter enemies, Newton and Leibniz. Actually, that's much closer to them than one might think. So then I came up with this idea to say this was my inspiration from Leibniz to express it in that way.
Mm-hmm. And yeah, can you expand on this aspect you mentioned about it being kind of very difficult to get the right value of it, like the physical implications of that? Or is that something we'll come on to more later?
Yes, we'll come on to that, we'll see it. Now, what I'm a little bit worried about is what are the next slides? We may have to get Puya. Did you give them back to me? I don't know, let's see what comes next, because it might be better. Have you got the ones that, well, we can go on to nothing but ratios, yes.
Was it the latest ones you sent by email? Or,
what?
Yes, it is in the latest email.
This is okay.
Should we try and find the ones from the late? Was it to me and Mia?
Yes, it was the one I sent this morning.
This is the most recent one.
This is from this morning.
Oh, it is this one. Yeah. Okay, good. But I thought, anyway, that's fine.
Is this okay?
Yes, so, yes?
Yeah, one second.
Oh, yes, so, very important, yes.
So you said that you would have discovered something like the Big Bang before Hubble made his observations.
Yes.
So could you elaborate on what dynamics you're exactly trying to simulate and run.
Sorry, what?
What dynamics you're trying to simulate and run in reverse to?
I'm saying that if you just time, they are Newtonian solutions, and if you time reverse them, they start with the absolute minimum of that quantity on the previous slide, and then they just structures form. You can get to any structure you like. There's a Newtonian solution that starts from maximal but not perfect uniformity. The very interesting. One of the great problems that led to the theory of inflation and so forth were, where are the seeds for the formation of large-scale structure? Well, in Newtonian theory, they're there from the word go. And so you can go from the most uniform shape that any number of particles can have to any other shape. So you can specify, if you like, globular clusters and spiral galaxies and things, and there will be a Newtonian solution that takes you there. And on the process, it will go through a state that at least qualitatively looks like the state after inflation has ended.
So to build on your point of inflation, I think the reason why people buy into a theory like inflation is because it not only explains the expansion of the universe, it explains why the universe is so big. Because if you trace back the evolution of the universe, you'll find very quickly that there are large regions of the sky that weren't in causal contact when you go back to the past.
That's the current theory, but if we're right, the current theory may have to be revised.
So,
relooked at.
If you do encounter this collision, you'd have to do it.
Can I say one other thing?
Yeah.
When you say the universe is very large, that's presupposing an external ruler. It's all ratios. If you say there's only ratios, nothing but ratios, it's just the distance between you and me. If my head is the ruler, then there's a certain distance there, but you've nothing but ratios. Nothing but ratios count.
I absolutely agree with that. I think we do have a ratio, except we have a ratio in time here. The snapshot that you see of the cosmic microwave background is as it was 13.6 billion years ago.
I would say, well, first of all, to go right back to where the evidence is, the evidence for the cosmic microwave background has been obtained with incredibly special instruments here on the Earth, and the results are recorded black ink on white paper, so to speak. So I think that's all got to be borne in mind. So many things are now taken for granted because it seems to work. I'm not denying it works very well, but there's an awful lot of big issues in cosmology, you must agree. dark matter, dark energy, all sorts of issues with that, yeah.
So last question. On the issue of dark energy, I think why we like dark energy so much is because we can explain things like galaxy clusters being bound together tightly, while the relative separation between galaxy clusters increasing over time. So in your point particle theory, are you thinking of every atom as your point, every galaxy cluster as your point, every star as your point?
Well, no, the galaxies would be many points and things like that. But this is early stages for that. I think a better thing would be to see what can be done with what I'm rather outrageously calling the principle of creation. But certainly, so every shape exists in the Platonic realm, in a mathematic Platonic realm. So there's no problem with whether such things can exist. The current story, we'll get onto a quotation from John Bell, if it is on these slides, where John Bell talks about distributions of fermions, where when he's talking about his Beerballs are just the distributions of fermions. So there's no whether it would all work out is another matter, but that in principle it could is certainly. There's no shadow of doubt it could in principle work. No doubt about that.
Yeah, thank you.
Yeah, it's the question how you get the observations.
Thanks.
Yeah, but great. This is going to be very good, the debate.
Yeah. Any other comments at this stage, or we can carry on? I think we can
Yes.
carry on.
Well, I think I've already. So, nothing but ratios. This is just staggering how people don't realise this. I've already said, that my head is smaller than my body. My body is not as high as this room. This room is not as high as the whole building. It goes on like that. You never get away from ratios, and you just don't see that much in physics. Not emphasized. I don't see. For example, well, first of all, I've quoted Einstein here, but just think about the foundations of general relativity. The key concepts are absolute proper time and proper distance. These are a fiction. These are things they're not ratios. They presuppose an external clock and an external ruler. That's highly suspect. And then Einstein himself says that he should have had he called it a sin that he hadn't done that. He never did a damn thing about finding how rods and clocks emerge from it. That all emerges beautifully in the Newtonian theory. I've worked that out with collaborators, where it starts very uniform, but with a thermal velocity, and then as the evolution goes on, clusters form, and above all, two pairs of particles orbiting each other in Keplerian ellipses become rods, clocks, and compasses all in one, and they all synchronize better and better. This is the complete inverse of what you think of from all the entropic ideas. Order emerges out of disorder, and it gives a theory of rods and clocks, which general relativity has got nowhere near creating yet. Nowhere near. So I think that's food for thought.
If ratios are so kind of fundamental and being neglected, why do you think theories like general relativity work so well, given that they aren't based on ratios as a basis?
Well, when you go into the mathematics of it, I would say it's hidden within the mathematics to quite an extent. There's a very beautiful. I have interacted with Jimmy York and his first PhD student who did very important work on solving the initial value problem in general relativity. And you can't do anything in general relativity without having initial data which satisfy the constraints. And those constraints, well, in Newtonian theory, the simplest example is vanishing angular momentum and vanishing energy in Newtonian theory. So that's quite a step to, but you're still, it's very wonderful in general relativity how a Riemannian three-dimensional geometry emerges out of two conformal geometries where there is not yet a definite geometry, but it's the slight difference between them that gives rise to it. It's a process that I call best matching, which is how that emerges. But I'm now going much, much further and suggesting we can create the shape we can create shapes in a way without having to do that.
So would you say that kind of ratios are implicitly being used in a powerful way in general relativity, but kind of not at front and center, and then you're kind of trying to get rid of everything else?
I would say it's hidden away, it's halfway there. But the reason why general relativity works is that a hugely important part of it has nothing to do with time. It's just the G naught naught in the field equations, the G naught naught terms do not contain time. They're elliptical equations that hold entirely across space. And that's not, that only, well, Lichnerevich, the Frenchman, became aware of, made some progress on that in 1944, but the real breakthrough came with York and Americo, with whom I interacted for 10 years, Americo, the Irishman. And so that's a very different way of looking at general relativity. Okay, shall we, yeah.
One second.
So about this point on G00 not having,
sorry?
About G00 not having a time component, I think general relativity takes symmetries very seriously. So your Killing vectors are directions around which you can do things. So wouldn't you say something like the energy being conserved globally is a precursor for the emergence of time? Like you would recover a notion of time because there is a symmetry associated with the conservation of energy?
I wouldn't. Well, first of all, a killing symmetry is killing the most of general relativity. It's so special that if there is a killing vector, it's very special. But in fact, my collaborator Tim Kozlowski, who you'll see his photographs later, he has shown that really general relativity. By the way, all of this I have to thank Dirac for this. So Dirac in 1958 wrote a paper, General Relativity is a Hamiltonian Dynamical Theory. And in it, he said, if you're going to quantize general relativity, and also in another paper in 59, you have got to restore the notion of simultaneity. Because if you just have arbitrary foliation invariance, you're just introducing random functions. It's just like doing Newtonian dynamics in a non-inertial frame of reference. You're just introducing random confusion with these arbitrary functions. So he said, on the basis of general relativity treated as a Hamiltonian theory, I'm inclined to believe that four-dimensional symmetry is not a fundamental feature of the physical world. Now, my collaborator Kozlowski, building on the work that was done earlier by York and Amuriko, basically he just shows that you have a shape. It is a non-Euclidean geometry with matter in it, but it defines a shape, and that shape just evolves. And there's just 1 degree of freedom. We'll come to that. There's 1 degree of freedom in addition. It's not a geodesic theory on conformal superspace. There's 1 extra degree of freedom. And all the structure in the universe, according to general relativity, comes from that 1 extra degree of freedom. Yeah?
Follow-ups later.
Great. Shall we continue?
Right. Yeah. Oh, well, I've already said yes. Right. Now, this is where... Now, there are things called central configurations or relative equilibria in Newtonian theory. There's a serious study of them. They're mathematically of considerable interest. So a central configuration, the expression was coined in 1899. It's in the Newtonian n-body problem. You have n particles, and it is such that the net gravitational force exerted on each individual particle by all the others points exactly towards the center of mass, but with a strength that increases linearly with the distance. And if the particles are initially at rest, they will form, it is said, they will fall homothetically, that is, without the shape changing, until they all collide at a point. Now, that is all in terms of an external ruler, because the shape doesn't change. So if you just say shape is count, nothing happens. But the much more significant thing, which was already discovered then in 1907 by Sundman, is that you can have these things where the shape does change. So the shape changes, and it becomes, and then it becomes, in the three-body problem, it becomes an equilateral triangle or a collinear configuration. And if there's n particles, the final shape is very uniform. It's a critical point. If you go back 1 slide, possibly, no, another one. Sorry. If that quantity there, which it's defined in the space of that V is a thing. If that is at either has a value that's a minimum, a local, or a saddle, that's a very special shape there. So that's where these total collisions can happen. But what Sundman showed, and it's a phenomenal piece of mathematics, virtually unknown. He showed that the system must approach this special shape, and moreover, that quantity, which they call the shape potential or the normalized Newton potential, it has a Hessian, the second derivatives, and virtually all the solutions must come to what they call the total collision along the eigenvector of that Hessian that has the largest eigenvalue. So it's an incredibly special theory about which virtually nobody knows anything except just perhaps 50 or 60 specialists in Newtonian gravity know about it. So we can go forward again. Instead of having those total collisions, they can stay in balance. So one possibility is what's called relative equilibria. So if you take that quantity that I've called the variety, if you say that that's a scale invariant potential, it's a product of the Newton potential multiplied by the root mean square length. Now, if you take that as a potential, then you derive forces from it. From the Newton potential, you get Newtonian gravitational forces. From the root mean square length, which turns out to be equal to the center of mass moment of inertia, you get Hooke-type forces. And you can either treat the Newtonian as repulsive or attractive, the Hooke-type ones as opposite, but they will be in equilibrium. So you have situations, this is very close to the absolute minimum, where you can interpret that as an equilibrium where the Newtonian gravitational forces pulling the system towards the center is in equilibrium with Hooke forces, which are repulsive. But you can equally say just as well that it's the other way around. And this incredible sphericity, this is very fascinating and leads to me hoping that we really might be somewhere, is that this is a unique property of Newton's shell theorem or the Newton potential theorem. So if you're outside a perfectly spherically symmetric body, the force you feel is if the entire mass was at the center of the body, or if you're within the body, it's the mass within the shell that you're at there. And this is a unique property with the 1 upon r potential balanced by the Hooke things and in three-dimensional space. And it leads, in this case, I think, to something like the cosmological principle. So the cosmological principle says, if you look around in a large enough region, it everywhere should look the same. So I like to say, take a dime and put it on top of this thing here. By the way, this is an equatorial slice through that incredibly spherical distribution there. This, I think, is for 5,000 particles. If you put a dime down there, which is, say, about a quarter of the diameter or a fifth, basically the structure that it will cover is basically the same. So I think you'd agree the cosmological principle is a holy grail of cosmology. It comes straight out of this. Looks very promising. So that's the balance there. Now,
so the way that the cosmological principle comes out, so yeah, the principle is that the universe kind of looks the same in every direction.
It looks the same in every region. It's the same, yes.
And you're getting this from a when does the homogeneity kind of?
It's just Newton's potential theorem does it, and so in the sun, it's the normal interpretation is the gravitational force that would collapse the sun is balanced by the kinetic energy of the heat in the sun. Mm-hmm. But we're getting the same effect without any motion. So there's no motion involved in this balance there. Now, you can have these things in 2 dimensions. You can have central configurations in 2 dimensions. And by far the most beautiful example is Saturn's rings. So Saturn's rings, the gravitational force is held in balance by the centrifugal force of the particles in the rings going around. So that's a beautiful thing. Now, another thing which is very interesting for this, who knows how the first attempt to explain atomic structure? Any volunteers? Yes, J.J. Thomson. So after J.J. Thomson discovered the electron, he tried to explain atomic structure. He invented what's become, he didn't use the expression, what's called the plum pudding model. So basically his model was a uniform sphere of positive charge and negative electrons held in balance. and that's now called the one-component plasma, still plays some role in things. But it was, by the way, I got his paper, and he does actually mention Saturn's rings in that paper. The first attempt to explain atomic structure was using these ideas. So that's, I think, interesting. So that's pretty interesting, I think. So I'm glad to see you nodding. Right, let's go on to the next slide. Now, this is the remarkable discovery. Now, everybody in physics is interested in absolute minimum because of absolute minimum of temperature, where interesting structures form. So it had been known theoretically, certainly in the 40 years ago, it was known that the absolute minimum of this quantity that I've called the variety would be very, very uniform. And certain predictions were made about it. But incredibly, nobody had asked it, what does it look like if the value of the variety is a bit above the absolute minimum? So I had meanwhile had this realization about the time reverse of these total collisions is a Newtonian Big Bang, which hadn't occurred to people working in the field. But I discussed it with my friend Alain Albuy at the observatory in Paris, and he got a student, Manuel Izquierdo, to do that. So to see how it's very difficult because of that specific details I told you about the Hessian. There's no real proper Cauchy initial data, but the best he could do to try and model this thing on my behalf, he had a student, he was going to do a doctorate on it, to do how the Newtonian Big Bang start. And the first step was to get two central configurations and use them to make initial data. So that was the idea. So Manuel was given the task to find central configurations just a little bit above that. And this was a huge surprise. It's a significant discovery in Newtonian dynamics, been hiding there all the time.
What were you expecting to see for the just above minimal variety structure?
Nobody had thought of asking. Nobody had given it any thought. It was a complete surprise. All these great experts, I mean, some terrifically high-powered mathematicians, nobody had thought of thinking, what's it like a bit above the minimum? And lo and behold, this comes out here. Just look at that.
But is there another kind of structure you might expect, like something kind of more uniform maybe, or?
Well, because of the absolute minimum, the minimum is always going to be very uniform. Now you'll see a bit more what happens, but I mean the statistics is I mean there's endless chances. So you get all these closed loops. This is in 2 dimensions, which is probably the joy about 2 dimensions is you can see the structures, but of course it's only in 2, and it's realistic it's got to be in 3. But you can say, what are the probabilities of, when you have a closed loop, of there being 0, 1, 2, 3, 4, 5, 6, 7, 8 particles within it? So there's incredibly rich statistical stuff there. The shape statistics is infinitely richer than statistical mechanics, this quantity is the analog of the total energy in statistical mechanics, and you can deal with things at or very near the maximal entropy. But there's nothing like this in statistical mechanics that I'm aware of. It's just a completely new thing. So now the interesting thing is, before this discovery had been made, I had predicted that all the smallest separations would be more or less the same, and they are. So the reason is the following. Suppose the law of the universe is it's got to start maximally uniform and then get more richly structured. How do you get from there to there with an increase in the value of my variety function? Well, one obvious way is to put 2 or 3 particles closer together, and then you will increase, because of that William Tell holistic effect that I showed. Well, it's just the 1 upon R, things like that. But then you stop and you remember Boltzmann said the great breakthrough that led to the the expression for entropy S equals K log W was Boltzmann in 1877, when he said, if I have molecules in a box, there are vastly more uniform distributions than non-uniform ones. Now, in this way, it then occurred to me there are vastly more ways to increase the complexity by changing all the separations on the left to here. So you've got that. So now you've got this wonderful thing. Instead of heat death coming out of this thing, as Boltzmann's insight implied, is that you will get structure, and moreover, you will get very special structure, remarkably structure. You get these filaments. So it's a complete inversion of heat death and all that stuff there. And let me just say about thermodynamics and heat death. People just forget how thermodynamics came into existence. It was all because of Sadi Kano studying how steam engines work, how to work out the maximal efficiency. And that's, if you look at all the work that was done developing both the laws of thermodynamics and statistical mechanics, there's always implicit a box. You have particles that bounce off boxes and things like that. It's all in a box. And believe it or not, I think there's only one person before me who asked, what happens if there's no box? And that was Boltzmann, and it was in a footnote in a debate he was having with Melo. But it's completely different if the system is not in a box. And the Newtonian n-body problem is not in a box, because the size can grow without limit. So
did Boltzmann consider the question, or just footnote
just
the question?
As a footnote, because he was all... Zermelo had been put to attack him by Planck, who hated the idea of atoms at that stage, and he was relying on the Poincaré recurrence theorem. So Poincaré recurrence says, if the solutions can explore only a bounded region of phase space, the system will come back infinitely often, arbitrarily close to any earlier stage. So Zermelo said, that means you cannot have entropy increasing forever. And this, almost in passing, Boltzmann says, are we so sure that, I can't remember his exact things. He certainly says, are we sure the momentum can't go unbounded? And I think he also says, is the universe unlimited? And the only place that I know where it's seriously put as a qualification is in Gibbs's great book, published at the end of his life, where he develops all this wonderful theory with Gibbs ensemble and spreading of the conservation of phase space volume, where he says, I must put a caveat. My system will fail if the system can expand into unbounded space, unlimited space, or the momentum can grow to infinity. But he doesn't say what you might be able to do in that case there. So, people just haven't noticed that. I've read a lot of... Has anybody here who's read the literature on the arrow of time ever seen that qualification put in? I haven't seen it. So it just shows... my son in Paris, he's a brain physiologist. He says it's just staggering how scientists do not consider the foundations of their theory. I think he's got a point.
I'll also just comment we're planning to wrap up at 7, so that's in 15 minutes time. So yeah, we have another 15 minutes for getting through some more content and discussion.
Yeah, so go on to the next one. Yeah, so now, yes. So now this is one, filaments with a, so this is some connection with art. So everything, I say everything that we know about the universe can be understood in terms of points in space. We can model it. So here is one of these things where so the question is consciousness. I say it's a gift. So this is a pointillist painting here, and here, so I've said consciousness sprinkles qualia, colors or sounds, on points that define that the underlying structure is, there's an underlying mathematical structure, but then consciousness puts these wonderful colors and sights and sounds and everything on top of it. And by the way, it's a nice story about this. It didn't quite work out. Puya, who's working with me, and Tim Kozlowski, said we could match these bridges perfectly if we could invert that one there and have the red thing going up to be the bridge. And then the one below, it would even match with the separations, because the one that would then become the bridge has the smaller separations and the one underneath you see has the wider separations. But when we tried to do it, it seemed to jinx my system. So we didn't get it. But I think it makes the point that it just ties in some ways, I think it ties mathematical structure with art and all our experience. And I do, when the great pianist Maurizio Pollini died, I read his obituary, and apparently for many years he refused to play Bach. He was a pianist, because he said Bach didn't write for grand pianos and things. But then he changed his mind, because he said Bach really, the essence of Bach is the structure of the music, so it's fair enough to play it on any instrument. So I think that's interesting in that connection. So we can go on to the next, Maria. No, we are on the wrong slides. Can you go forward? Can you go forward fast, please? More, but my collaborator Tim Kozlowski. No, even more. And we'll have to come back to that. Even more. Now stop. Now I want to show you why I think we may have stumbled on a theory of creation. So the etymology of creation is nothing to do with creatio ex nihilo. It's from the Proto-Indo-Germanic word to grow. And I'm going to illustrate this now with 12 slides. So this is a colleague of ours, Hemant Shukla, did these. These are just 100 particles, equal mass particles. And the one on the left is either at or very close to the absolute minimum. And then the next one up, we've taken that as, so now we introduce the notion of age. So by age, we mean the difference between the actual value of the variety taken away its absolute minimum. So everything starts from the absolute minimum. That was when the universe had age 0. And so if this is the universe that its age is 0, this is a little while later, and we take that difference there to be age 1, and then the ages go up. And you see, structure is growing. It is growth of structure. You come along here, and already here, at this stage here, you've got something that looks like a pair of spectacles. You get circles appearing. So that's quite interesting. We've got, I think this is a theory of growth, of structure creation, of there. Let's go on to the next one. So this is now ages 3 to 5. Now look, you start getting these filaments appearing. So these are these continuous curves that might have led Leibniz and Newton to create the differential calculus. But because they look pretty continuous, if you're a bit short-sighted, they are. So those you see over there, there's 2 conjoined circles, a bit higher. Yeah, those are 2. Now, if you go back one, you see that those scissors, you could say that those scissors have become fossilized and are now the conjoined circles in the next one there. So in some senses, at this age, you're getting records, sort of fossilized records of younger ages of the thing. So and then the other thing which is very striking, which Puya pointed out to me, is that these filaments bifurcate, just like the filaments branch in the way growing plants and trees do. And then the parts of any shape are always less structured than the whole, but they at least have the potential for containing records. Now, I say I mean, I think it is widely recognized that if you could take a snapshot of the universe now, or a sufficiently large region of it, and just have the record of the separations of the fermions in that snapshot, that encodes the whole history of the universe and the laws that generated it from the Big Bang, all in one thing there. And it relies on what I call explanation through time, some rather ill-defined initial state. There's very obscure understanding of the Big Bang in general relativity at the moment, as opposed to the Newtonian one, which is completely understood. That from that, instead of having to rely on that evolution from an ill-defined past, you create it all with just with just asking, saying, I want a shape with a particular value of the thing. These are all ones that correspond to these central configurations where the complexity, where the variety or the complexity is critical. It's either a minimum or a local minimum or a saddle. But there's a huge, we'll see, there's a huge number that are very like it that are not that. As we'll see in a minute there. So let's go on to the next.
You're saying that you can get all the laws just from the separations?
The conjecture is that the whole of physics as we understand it now could be deduced from the separations with an appropriately chosen scale invariant function. We certainly can't do it with the one we've got. Remember, the one that I've shown you and derived is the simplest one that you've got. There's but you can add things like charges and color charges and things like that. So that's the proposal to do that. Yes, look at that. So first of all, there's definitely a very easy theory. I'm convinced that there's a very easy theory to understand how these shapes form, and then it can be tested, and it is being currently tested by a student in Lisbon called Maria Violaris, who's got access to a supercomputer. So my conjecture is it will be possible to create, first of all, what I call monomers, what look like one particle pushing its neighbors away, and then there will be dimers where it looks as if two have done it and three have done it. And we will be able, I think, the conjecture is we will, without any quantum mechanics at all, and with a very simple theory, we can predict what shapes will form as the complexity is increased, and that then can be tested in a matter of weeks on the supercomputer in Lisbon. And that so it might make the task of quantum mechanics explaining shapes of molecules just so it was all going in the wrong direction. Now, this is a huge claim, so I think at the Royal Oak we better do that. So those who want to check this claim, so the most outrageous claim of all is that there is no quantum mechanics at all, that there's no need for a wave function. I don't know whether we just try very quickly to get that, or what do you think? We've hardly got... Well, I'll just briefly say it. I've got about 5 minutes. Yeah. So I set out in my book, The Janus Point, to write I proposed a time-dependent Schrödinger equation that would give probabilities for shapes that change as this quantity, the age, increases. And so with my collaborator, Kozlovsky, who is somewhere in the pictures, I think we shot past him and it come back again. Well, first of all, I realized that it would have a unique solution. That's to do with the fact that the variety or this quantity, the key quantity, has an absolute minimum and it's positive definite. The solution would be unique. Then we realized that for all values, for all shapes that have the same value of the variety, the wave function would have the same value. And my immediate reaction is, well, that's a trivial theory. And Tim immediately said, because it doesn't seem to be anything there. But Tim said, no, that's not true, because you have to have a measure as well. So in fact, shapes have, there's a measure on the space of all possible shapes. And my theory had predicted a wave function, the values of the wave function. Then you find the Born type density, the Born density that goes with it by taking the squaring the wave function. And lo and behold, it's already existing there. There's already a Born type density on shape space. So I think that is thought-provoking. There are probabilities for shapes. So, is there any need for quantum mechanics at all? So you can find that there's at least one, there's a debate with me on my website, platonia.com, with Seth Lloyd, where I'm arguing about this. Seth said you'll never get the carbon molecules, but I suggested we might. Certainly the shapes are out there. It's just a question of whether we can find the right scale invariant function that will generate it. But the main fact is there are probabilities for shapes, and if you set up, so when the whole problem with the Wheeler-DeWitt equation and the problem of time emerged, Bryce DeWitt was trying to find a wave function that would give probabilities for configurations of the universe. So I just made one change. I said I want a wave function that gives probabilities for shapes of the universe. And the theory is perfect. I mean, Kozlovsky, Tim, my collaborator, he's a much more well-founded theoretician. I mean, knows his theoretical physics much better than me. He says it's exactly what you would expect doing standard quantum mechanics. And lo and behold, you find you didn't need to do the quantum mechanics at all. You get the answer without the wave function, because there is a Born type density for shapes.
So if your theory works, what does it mean for quantum interpretations, like the measurement problem and Everettian quantum theory? What happens to these
I would say it just
consequences?
disappears. I mean, where is the measurement going on? We're sitting here chatting happily. Where's the collapse of the wave? I mean, this wonderful opening of John Bell's paper, Quantum Mechanics for Cosmologists, you know. When was it that the universe first felt it could collapse its wave function? Was it when there were sufficiently active microbes, or did it have to wait until there were sufficiently qualified PhD students for there to be a collapse of the wave function? I mean, I'm getting to the stage now where I'm a bit inclined to say, tell it to the Marines. I mean, the collapse of the wave function and the observer and so forth, I mean, what I'm suggesting does sound outrageous, but I don't think it's any more outrageous than quantum mechanics. One other thing I will say is that one of the huge issues in quantum mechanics is entanglement correlations, which seem to be set up instantaneously. You can't send information with them, but they seem to be established instantaneously, the entanglement correlations. No time is involved in establishing.
Are they not established when the systems that become entangled
No,
interact?
but the idea is surely that Alice and Bob think they have free will to set the position of the thing, and then they collect statistical data here and statistical data. Later, those statistical data are brought together and they're shown to be correlated in a way that currently only quantum mechanics can explain. Now, there are correlations which nobody thinks is mysterious. These are the correlations between points in Euclidean space. You have points in Euclidean space. There's n times n minus 1 divided by 2 separations between them. There are n squared correlations. Nobody thinks they're mysterious. So if we're right that there's no quantum mechanics and it's all about ratios of separations between points in Euclidean space, that's where these miracles of entanglement could come from.
So what would your theory say about what's happening in the Schrödinger's cat experiment if it was done? What happens to the cat, and what happens when someone observes it, and so on?
This theory is a little bit like many worlds, but it's many shapes. So I would just say there's one shape in which the cat is alive and one in which it's dead.
So both those shapes are kind of in
but
existence.
the whole story is there, because also there would be the records of Schrödinger being thoroughly nasty and putting the poison capsule there. You know, I mean, all of the records will be there, as they are. I mean, what I said right at the start, all the evidence on which all of this fantastic structure and supposed understanding of quantum mechanics and the universe, it's all encoded here in the separations of fermions in solids. So if you can explain that structure, you can do without collapse of the wave function. There will certainly be two different cats because there are many different shapes. So instead of being many worlds, there will be many shapes.
Mm-hmm. So you get the same kind of the same description of what happens as when you use. So say you want to apply the laws of quantum mechanics to describe a certain situation. Your theory would also predict the same outcomes, but it's saying that the ontology, instead of being the wave function, is the kind of real part of reality that's leading to these equations working. It's actually the shapes of the underlying real thing.
It's just the shapes that will be it. I mean, of course, we're a huge distance from really doing anything like that. Mm-hmm. But I mean, quantum mechanics is huge. Michael.
So the non-separability
1 second.
Really,
sorry.
it's okay, I think I can be heard. Okay.
You won't be heard.
Well, really, I think I can. You can hear me, can't you? Okay. If people really want me to use this, I don't think it's on, is it?
It's for the recording.
Oh, I see. Okay. Well, yeah. Yeah, I'm so sorry. I've forgotten my question now. I'm sorry. No, so the non-separability is really is cashed out in terms of consistency of records, where the consistency of records is simply mandated by the fact that you've got this correlation coefficient between the points, between the configurations, which is underpinned by the story that you've just told about the way that the shapes effectively emerge, and the consistency of the records is as reflecting this condition on the shapes and their relationship.
Yes,
it's emerging. It's all basically contained within the level of pure statics. There's really no dynamics at all in this.
There's no dynamics at all.
There's no dynamics at all. There isn't even really, in a sense, kinematics. There's really just a kind of a hugely deepened version of statics. In the sense that the Greeks understood.
Yes, I suppose
in the
you
sense
could.
That if you go back to the very beginning, what you said about ratio and proportion is very interesting. Because remember that Eudoxus thought that the whole of mathematics essentially was the theory of ratio and proportion.
Yeah, well, of course, that's what rational is to do, isn't it? Yes, as well. Yes. No. I mean, I think in some respects the Greeks got a lot right.
It's an incredible vision.
Yes. And but I mean, this is, it will be very interesting. I mean, Maria in Lisbon, she's got a very supportive, she's taking a gap year, but they're allowing her to use the supercomputer in Lisbon while she's doing that. She's really doing impressive analysis. I mean, she's got one of these central configurations of 1,000 particles in 3 dimensions with about 15 or 20 filaments with up to, I think, 25 particles in one of them. She's worked out that 22% of the particles are in filaments. She's worked out statistical properties of the things. There's just a colossal amount. And she did that all in a few weeks. She then had to take her master's examination or evaluations, but now she's taking and actually she's in. I had a 3-way Zoom discussion with her and Manuel, the Spanish chap who made the discovery in Paris, and giving her tips. What you need is not a CPU but a GPU, he said. Then you'll go twice as fast or whatever it was. But I mean, it'll be fascinating to see what comes out of there. And it's. I don't think, and this is, so far as I can see, this is totally and completely new in physics. I don't think there's anywhere else that anything like this is being done. And we stumbled on it.
It's very interesting, though, to see what you were saying about Dirac's work in 1958 and putting GR into the Hamiltonian setting, his motives for that. Because it does seem to be there is a connection there.
Yes, well,
it says he was also trying to see how things would look if there were no dynamics.
Yes, I wonder about that, but he was, I mean, Dirac, for me, in some ways, I have to thank Dirac for everything. It was thanks to Dirac when I was trying to talk to him and he would have sent me packing that I was able to buy that marvelous house where I live now. But he just mathematically analyzed the thing. I don't know that he was terribly contemplating these sort of things that philosophers of science get to. No, it was just very grabbing hold of the mathematics and seeing what the mathematics says. No, I mean, he's all right. I mean, we haven't got on to the arrow of time and things like that, but I do have one technical contribution I made to general relativity, which is just this one arrow of time. The universe is not described, if you are going to go back to dynamics, the universe is not described by a geodesic principle. There's just one more degree of freedom, and that one extra degree of freedom is always making, if there is a dynamical thing, the universe seek a more structured state. Just one extra degree of freedom.
Yeah, so I have a question on this arrow of time topic. So you mentioned earlier that everyone talks about how we're heading for a heat death, kind of based on the conventional view of entropy and thermodynamics. So according to your approach to the arrow of time, what would you see as like the direction we're heading in the very, very long-term future? If not a heat death, then what is happening?
That's good. So first of all, there's a huge difference between, so all of that I've said today has been that the finite number of particles, n. There's no limit on it. But Leibniz insists on a sufficient reason for anything. So what reason could possibly be given for the value of n? It's got to be at least 3, but that's, the three-body problem is already very interesting, but it's not very interesting really. So the only rational, the only thing that you really want is somehow to extend this theory to infinitely many particles. And we have got quite some way we're doing that. I think it is possible to do it, and it will rely crucially upon three-dimensional space and the Newton potential theorem, this balance there, that as the complexity increases, it will get, Tim summed it up when I said we need infinitely many particles. He said then there's infinitely many possibilities. I would say when the universe as the universe gets older and older, its structure gets richer and richer. And in fact, I mean, to some extent this is true. I mean, when I was born, I had, very smooth skin and no hair. I mean, I'm beginning to look a bit decrepit, but I've got much more structure in me now, So with infinitely many, so if you've only got a finite number of particles, it goes into limit cycles. You get these Kepler pairs forming, rods and clocks, but after a while, nothing particularly new happens. In the Janus point, I say the needle gets stuck. But I think it's going to be completely different if you allow for infinitely many particles. And so I think it's everything to play for. And that's the only satisfactory thing. I mean, Leibniz is just such a source of fascinating ideas and so on.
Great. Yeah, happy to hear an optimistic view on the end of the universe instead of the usual heat death ending that everyone seems to think is inescapable.
But I mean, let me say again, I think, is it really true that after Boltzmann, I'm the first person to ask, should we be thinking about the universe in a box? Does anybody who studied the problems with the arrow of time come across that? I've not come across anyone who said that.
We can pose it to our online audience of people watching later as well. If anyone has seen it, then post in the comments.
It's what my son says, It's staggering how little thought working scientists pay to the foundations of their work.
The box is a natural emergence of cosmology. So the box naturally emerges in cosmology because light has a finite speed. So what you're thinking of as a box is the particle horizon of the universe. where you can't communicate beyond.
I agree.
Yeah.
So of course there is this thing with the expansion of the universe, but there are uncertainties about that. But well, first of all, you will read everywhere that life is going to get desperately boring because the densities go to zero. That's meaningless if you say nothing but ratios, because it's just ratios of things. So it could be, at least it could be possible that these black holes that evaporate, that then, sort of, shall we say, spidery structures, spider's web sort of structures form. And then there's the question of, let me here quote, so one thing I think is worth quoting is the one-sentence abstract of Heisenberg paper where he creates matrix mechanics. He says, an attempt will be made to create a mathematical framework for quantum mechanics that involves nothing except quantities that are in principle observable. But when you look at what those quantities are, they are energy differences and transition probabilities. They're not raw data. So the raw data, have a look at when you get, I've got a book at home, the title is The Shape of Molecules, and it shows you how actually you get the structure of molecules in scattering with light experiments. It's incredibly special structure. You've got the book was published in about 1950. There's an old-fashioned light bulb there producing light. Then it has to be collimated. Then it goes through the prism to split it up. Then there's an emulsion over here where it's on there. It's incredibly complicated. And in the rest, is there anywhere else in the rest of the galaxy, or possibly even the whole universe, where there's such special structure as that? I wonder if there is. A few years ago, Anton Zeilinger gave a talk here about all these incredible experiments he does. And I said to him, is it possible that this very special equipment that you're using is in a large part creating the results? Oh, no, he says, I can buy that for a few $100s, he says. But come on. I mean, Harvey Brown, who apologized for being unable to come this evening, said the first thing he did when he came to Oxford was neutron interference, two slit things there. He said the precision with which these crystals had to be right was just staggering. I call these beacons in the universe. If somebody could fly around the universe who could see these incredibly special structures, they would stand out like Sirius in the night sky. And you wouldn't see them anywhere else. I think there may be a huge amount of, and that there's, well, that's in these things here. They're holistic. There's a complete, to understand this structure here, it's a statistic. So first of all, you have to say, so there's vast numbers of shapes that look just like that, but then to get the particular one, you have to look through all of them. So and it won't be easy to find anything that looks like those sort of experiments, the equipment that Anton Zeilinger or Aspect, all of these people there. It's an incredibly special structure from the point of view of the universe as a whole. What you can find, and I think our theory could explain, is the distribution of the isotopes, the uranium isotopes, and how much there. Those are the sort of structures that I think could come out of these things, but these incredibly special structures. Maria in Lisbon has no hope of finding those, but she might find things that look like, in fact, she has found something. She's got one thing with much higher value of the variety, and so it's a very tight bundle. Well, that's the way it looks. And then there's one or two particles, I think, further away from it. It looks to me like an evaporating globular cluster. That's getting like something that the universe looks like.
Great.
We better.
I think we should, wrap up. Thanks, Julian, for joining us and giving this great explanation of a very radical viewpoint, but with lots of interesting consequences for different aspects of physics, including the arrow of time, cosmology, and not needing quantum mechanics. We will carry on discussion in the pub, as we've mentioned. So we can, maybe debate whether we actually need quantum mechanics in more detail. This is Julian's latest book, The Janus Point, which I'm partway through reading with my Shakespeare bookmark, which is very relevant as there's lots of Shakespeare quotes in it. And this was the signature that Julian was referring to earlier in the conversation. He also has another book, The End of Time, if you're interested in reading the popular science.
The one I really would recommend is my book on the paperback, The Discovery of Dynamics. That was one marvelous experience. Mm-hmm. By the way, the big influence on me was Kepler. Yeah, we can talk about that in the pub.
Mm-hmm. Yeah, great. And thanks again to Mia,
who
organised
thank you,
the event.
And thank you both.
Thank you to Maria for being a great host.
Yes, no,
Thanks.
great work.
Yeah. Can I get everyone together for a photo before we disperse?